Unit 6 is on energy, and we've talked a lot about different quantities of energy and how we measure those, what units we use. But what do we do in the lab to actually determine these numbers? How do we know, for example, that it takes 4 joules per gram degree Celsius to heat up water? Well, we measure that with something called calorimetry. And in the word, you can hear the part calor, which sounds like calories or energy, and metry, which sounds like measuring. And that's exactly what calorimetry does. It measures heat or energy. So let's take a look at calorimetry and how we use it to measure energy. There are lots of different types of calorimeters, but we're going to take a look at the coffee cup calorimeter, one of the ways that we can measure the heat that something releases or absorbs. It's a common thing to use in the chemistry lab because you can make it out of coffee cups. And we're going to go part by part through this whole calorimeter until you understand exactly what's going on. Let's start with the reaction mixture. We're studying the solution of water, and we're going to mix something into that water, and we're going to monitor its temperature. So in the solution, we have water and substance that we're studying. What could we be studying? Let's look at a few options. Well, we could be studying cooling something. So maybe, for example, we put a hot piece of metal down into our water. That's actually what we're going to take a closer look at in a few minutes here. We put a hot substance down in the water. So maybe it's a glowing red hot chunk of metal, right? And what's going to happen is that water is going to warm up and that hot thing is going to cool down. And based on how much the temperature of the water changes, we can tell things like its heat capacity or its mass. We could also run some chemical reaction. So maybe we want to combine an acid and a base. And if we're reacting an acid and a base, that's going to release a bunch of heat, change the temperature. And based on how much it changes the temperature, again, we can determine things about that reaction. Or lastly, we could dissolve something. So if we just dissolve sodium chloride or ammonium nitrate, that'll change the temperature. And we can learn about the energy involved in that dissolution process. So what do we get out when we study these things? Well, if we study cooling something, or even heating something up, you could do the reverse. Typically what we're going to be getting out is the heat capacity. And that's what we'll actually calculate in this lesson. Or you could get the enthalpy. Remember, delta H is the enthalpy of a reaction. It's the heat released at constant pressure. And we could determine the enthalpy of a reaction with our calorimeter. We could determine the enthalpy of our dissolution process. So these are the kind of things we can find out with calorimetry. Okay, now let's go through the rest of the parts of this calorimeter. Next up, we got the thermometer. And we've already mentioned several times that we'd like to measure the temperature, because how much the temperature of the water changes tells us about how much heat the process in our reaction mixture gives off or absorbs. Okay, next up we got the stir. This makes sure that the temperature is uniform. What you don't want is to have something that's hot over here and then a little less hot over here. And so then we would not be measuring the correct temperature. And so that stir, as it rotates around or goes up and down, it'll move that solution around and make sure everything has a uniform temperature. Okay? And then lastly, we have the cover and our styrofoam cups. Notice there's actually 2 styrofoam cups stacked together, and that does a particularly good job of insulating this container. And it minimizes heat exchange with the lab space. Why is this important? Well, we're trying to measure with our thermometer all the heat released or absorbed by the process. And if all of this heat is just flowing out into the atmosphere, instead of being recorded by my thermometer, then I'm going to get the wrong answer. So the better we can isolate that from our surroundings, the better data we'll get out. Okay, now let's think about what happens as we run a reaction or mix something hot in. Specifically, in this lesson, we're going to focus on dropping in something hot. So say we drop in a hot chunk of metal. So it's bright red because it's nice and hot. And surrounding it is this blue water. Okay, well, what's going to happen? If we think about the temperature over time, the hot thing is going to cool down. So let's say the hot thing starts up here, and let's say our water starts down there. Well, our hot thing is going to drop in temperature over time until reaching some nice steady state. Meanwhile, our cold thing is actually going to warm up. Whoop. And at some point, those are going to approach the same temperature, which is what I have written in purple. So the final temperature of that reaction mixture is going to be the same, because the hot thing gets cold and the cold thing gets hot until they're the same temperature. And then at the end, instead of having cold water and hot metal, we have lukewarm water and lukewarm metal, all the same temperature in purple. Okay, so the hot thing cools down and the cool thing warms up. That's really important to keep in mind. All right, so let's say that we actually want to do this experiment. We want to drop something hot in, and we want to figure out what's going on. The first thing we need to think about carefully is the changes in temperature. And so we're going to go through two separate calculations where we just think about temperature, and then we're going to actually go to our final step of determining the heat capacity of copper. So our end goal here is going to be determine the heat capacity of copper by dropping it in our calorimeter. Just one of the many things we could determine with calorimetry. So in this case, we drop a hot piece of copper. Like I've said, we'll represent that as a red block. So here's our hot copper dropped into our water. And we know that originally that hot copper is 44 degrees Celsius. Okay. Now we're also told that the water initially, which we'll have in blue, is 21 degrees Celsius. 21.8 degrees Celsius. At the end of the experiment, the thermometer reads 23. Okay, so that's what we know. At the very end, this says 23 degrees Celsius. Now remember, because the temperature is uniform at the end, that actually means that the final temperature of our copper and the final temperature of our water are both 23 degrees Celsius. So what's the final temperature of the copper? Well, it's 23 degrees Celsius. How do we know that? Because that's the final temperature of the whole reaction mixture. So both water and copper end up at 23 degrees Celsius. So this is really just emphasizing the point I made on the last slide, that the hot thing cools down and the cold thing warms up until they're the same temperature. In this case, we know it's 23 degrees Celsius. Okay, next question to ask. What's the change in temperature for each of these? Okay, and we really need to know that to use these in our heat capacity equations, which we'll take a look at next. All right, well, the change in temperature is always equal to the final minus the initial. And that's true for water, and it's true for copper. So let's calculate it for both of them. And then in our last calculation, we'll use both of these values to help us figure out that heat capacity of copper. Okay, so what was the final temperature of our copper? We said that was 23 degrees Celsius. And we're going to subtract from that our original temperature of copper, which we know was 44 degrees Celsius. So notice here, I'm taking 23 and subtracting 44. When I do that, I'm going to get out actually a drop in temperature of negative 21 degrees Celsius. Totally makes sense because our copper was hot, it should drop in temperature. Let's do the same thing for water. Water, we know the final temperature, 23 degrees Celsius. It's the same thing. And we're going to subtract from that our original water temperature, which we know was 21.8. When I subtract those, I get the change in temperature, which in this case, because 23 is bigger than 21.8, we get a positive number, and it's positive 1.2 degrees Celsius. Okay, now you might notice right away that the copper changed in temperature a lot, and the water didn't change much at all. Two reasons for that. One is that our water is making up 300 grams of mass, where our copper is only making up 50 grams. So we just have a lot of water around, and so that spreads out the heat. The other reason is that the heat capacity of water is unusually high. And so very often our water won't change that much in temperature, and something else that we have in it will change a lot more. So those are the change in temperatures. Now we're going to take advantage of those to figure out the heat capacity of copper. Okay, so a hot piece of copper with a mass of 50 grams is dropped into 300 grams of water, and the copper's temperature drops by 21 degrees Celsius, while the water's temperature increases by 1.2 degrees Celsius, and we want to know the heat capacity. How are we going to solve this problem? Well, we're going to use our heat capacity expressions. And here's the key. Here's what we know. And this is why this slide is titled Thermal Equilibrium. Because what's going to happen is my copper, remember, cools down. And Q, remember, represents our heat. So this is just another way to write heat. Any heat lost by the copper, where does that go? Well, the heat lost by the copper goes straight into that water. So this allows us to write this really important equation. This is the key of our calorimetry calculations. We know that the heat lost by the copper is the heat gained by the water. Okay, where can we go from there? Now we use our heat capacity expression. Remember that we can say that Q is equal to CS M delta T. And that's just the heat capacity equation we've used before. So that means the heat lost by copper can be calculated by CS M delta T, and the heat gained by water can be calculated CS M delta T. So let's substitute that into our equation. Okay, so this is a relatively complicated algebra maneuver, where we know Q is equal to CS M delta T, and so we can plug CS M delta T in for both the Q for copper and the Q for water. That means that what we're going to get is negative CS for copper times mass for copper times delta T for copper is equal to The same stuff for my water. CS for water, that's the heat capacity of water, times the mass of water, times the change in temperature of my water. So this is a key equation that we use in our calorimetry to be able to solve problems. Notice we have floating around our heat capacity for water and our heat capacity for copper. Here's the thing. I know the mass of copper. I know the change in temperature of copper. I know the heat capacity of water. I know the mass of water. And I know the change in temperature of water, which means I'm going to be able to solve for my CS for copper, that heat capacity of copper, that whole goal. So this came from thinking carefully about how the heat lost by copper is the heat gained by water. Okay, let's finish out this calculation. So here we have our copper and water equation that we just wrote. And notice I put all those subscripts for water and copper on there, and that's because there's multiple masses and multiple temperature changes in this problem. So really important that we keep track of those carefully. The first step here is going to be to identify the variables given. Okay, so that means we need to identify the heat capacity for water, the mass of water, and the temperature of water. I'm going to underline those in blue. The mass of water, 300 grams. The change in temperature for the water is an increase of 1.2 degrees Celsius. And then we're given the heat capacity of water, that's 4.18 joules per gram degree Celsius. Okay, let's do the same thing for copper. We know that the mass of copper is 50 grams. And we know, right down here, that the temperature drops by 21 degrees Celsius. So those are all the variables we need. The only one we don't have is the one we want to find, which is our heat capacity of copper. So now I'm going to do some algebra to rearrange for the unknown. So I've done step 1, which is identify the variables we have been given. And now I'm going to go on to step 2, which is to rearrange for my unknown. My unknown is that heat capacity of copper. So the way I get all of these other variables over is I divide by them. So I'm going to divide by negative mass times copper times delta T of copper. So I divide both sides by mass and change in temperature. So mass of copper, change in temperature of copper. Okay, that means that my heat capacity's negative sign up there is going to cancel out, my mass will go away, and my change in temperature will go away. And I'll be left with my final equation, which will tell me that the heat capacity for copper is equal to the heat capacity. And here I'm going to use blue instead of writing the subscripts. The heat capacity for water times the mass for water times the change in temperature for water divided by, I'm going to use red for copper, the mass of copper times the change in temperature of copper. And now I'm ready to plug in those variables and figure out what my heat capacity of copper is. And don't forget that our negative sign came along too. So that's negative right now. Okay, so I'm going to plug in now the heat capacity for water. We know that's 4.18. I'm going to plug in the mass of my water. We know that's 300 grams. I'm going to plug in the change in temperature of my water. We know that's 1.2 degrees Celsius. And then I'm going to divide that by my mass for copper, which we know is 50 grams, times my change in temperature of copper, which we know is 21 degrees Celsius. And that's a drop. So here's what happens. This negative sign, which is here, and this negative sign, which is here, cancel out and make that a positive sign. So eventually those negative signs go away because one of my temperatures is dropping and one of them is increasing. Okay, so now I'm ready to multiply 4.18 by 300 by 1.2 and divide by 50 times 21. All right, let's do that. When I do that, I get out the heat capacity for copper, which turns out to be 1.43. And the heat capacity units are always joules per gram degrees Celsius when we're solving for specific heat capacity. All right, so that's the specific heat capacity of copper from my calorimetry measurements. Hey, hey.